but they will be discrete. Okay? And then you have minus K naught minus K1. There will be a set of modes here. Okay? And then this will be the track modes. Inside the dielectric slab, but these are the track modes that are outside. And the physics dictates that they will be like that. Now what happens if we try to, if I make H bigger and bigger? What happens to those modes? Do they disappear, they become denser, or they become sparser? Multiple choice question. How do they become denser? And if they become denser, how do they become sparser? If they become sparser. We should go back to something that looks like chapter 2, right? What happens if the two parallel plates are infinitely far apart? Would there be branch cuts associated with region, the top region and the bottom region? There will be branch cuts there, right? Right now there's no branch cuts because there are no top and bottom region, they're all metallic. Okay, so finally what happens is that the picture of this is that these modes will become denser and denser because these are outside modes. And there are infinitely many possible modes that can be trapped outside. And the number of modes that can be trapped outside becomes larger and larger as I make the spacing larger, right? But the number of modes that can be trapped inside doesn't change very much. They will be evanescent outside, so they remain trapped. So finally, the picture you get as the spacing gets very large is this picture with some trapped modes there. And then with the branch cut, with the other modes becoming branch cuts. With some track modes there. The track modes will not change very much because the track modes are evanescent inside. So when you start moving the plates outside, you don't see the metallic plate because they're evanescent outside. So they remain something like this. So this is a physical picture of the modes that you should have. Are there any questions regarding this physical picture? Okay, if no, then what you need to do in solving these problems then is that you need to solve this complicated geometry. And you'll find trapped modes as well as untrapped modes. Trapped modes are those that are trapped by the homogeneity. Untrapped modes are propagating wave outside. You'll find two families of modes and you can solve those regions and then you can do mode matching. The mathematics of mode matching is quite complicated, so I won't go through the detail. You can read about it in chapter 6. I'm sure that you can pick it up if you need to. Okay, I won't go through the detail of mode matching. But this is essentially the physics that you have, and you reduce a three-dimensional problem into a sequence of two-dimensional problems. And this is actually quite popular in a number of areas in optics as well as electromagnetics and microengineering. Okay? I have only 2 minutes left, so I wonder if I should start a new topic or just go on with this whole topic, talk a little bit more. So ask me any questions that you may have on this topic so that I can use up my 2 more minutes.
Well, sure. As you make the plates further apart, the location of K dot on the plane doesn't change. You just added more modes.
Yeah, K naught doesn't change because K naught is defined to be this number. Yeah, so the number of modes that are trapped outside becomes more and more. They become denser and denser. Eventually they line up like a branch cut. Essentially those modes become branch cuts when they're outside. Because those trapped modes will hardly see the two parallel plates and they remain essentially stationary as you move the two plates further apart. Okay? And this gives you the concept of mode conversion because say if you have a laser, if you have a laser coming in with the optical waveguide, say you have a single mode propagating well guided in this region. But once you hit this region, you go back to this problem, it will have a whole bunch of what actually is called radiation mode. Radiation modes, which are modes on the branch cut. Okay? Due to mode conversion, this single mode will convert into radiation mode, propagating in all directions. This is the trap mode. So this thing corresponds to this picture we have on the left. If you're clever enough to excite the laser, you only excite the trap mode. It will propagate for a long distance, but once you hit this facet in the laser, mode conversion will happen in the ray will spray in all possible directions due to this picture over here. Okay? And these are called the radiation. And in order to find the coefficient of the mode conversion, you have to go through the mathematics of matching the boundary condition. Find the reflection operator, transmission operator, and obtain the solution there. Okay? And then you can characterize this problem. But what is usually done is that it's very hard to solve an infinitely large problem, and people use either a periodic boundary condition here to make the mode countable, or you put EEC boundary condition here to make the problem a finite number of modes anyhow, but you try to make the region larger and larger, either using periodic boundary condition, PMC boundary condition, or PEC boundary condition to model this laser facet problem. And then you can use that to characterize what happens at the end of the laser cavity. You need this kind of laser cavity. High Q, there's very little reflection, but you form two of these facets. And then you get a high Q cavity, you can get this thing to laze. When it lays, then it leaks out energy on the side. And then it can give rise to your laser beam, like your laser pointer and that kind of thing. And you need to characterize this. Okay, are there any other questions? Okay, if not, then we'll continue again on Thursday at 9 a.m. Please don't come to class late.